Hi, I'm Emily, and I will be solving problem number 6 for my final project. So for the first part, if we suppose that vectors u and v are linearly dependent, then that means vector v can be written as a linear combination of u being multiplied by some scalar c. There are two ways to represent eigenvector v as a linear combination of eigenvector u. Using our knowledge that AV equals lambda v, we can multiply A to both sides and rewrite A in terms of lambda 1 and lambda 2, just so we can denote that eigenvector u and v have distinct eigenvalues. And then you can also simply just multiply both sides by lambda 2. And so you have these two equations, and you need to set them equal to each other and put everything to one side, and you should end up with this. So in order for this equation to hold true, the weights C1 times the quantity of lambda 1 minus lambda 2 must be equal to 0. This is because u is an eigenvector, and eigenvectors cannot be equal to 0 vectors. However, lambda 1 minus lambda 2 can also not be equal to 0, and this is because they are two distinct eigenvalues, and we all know that two values must be equal to each other in order to subtract to 0. So that means the scalar must be equal to 0. But earlier we did this under the assumption that u and v were linearly dependent, and so setting c equal to 0 would also make v equal to 0, which is wrong, because v is an eigenvector and eigenvectors cannot be equal to 0 vectors. So therefore we can conclude that the set of u and v must be linearly independent. So for the second problem, in order for an n by n matrix A to be diagonalizable, it needs to be similar to the diagonal matrix D, such that A equals PDP inverse for some invertible matrix P. So my approach to this problem was to construct a 2x2 diagonal matrix D with a 0 and one non-zero value in its diagonal, and to also construct an invertible 2x2 matrix P. So in my first example, I set the diagonal matrix D to have 0 and 1 in its diagonal. And for the matrix P, I set the values to essentially just be anything as long as the determinant, or AD minus BC, was not equal to 0, because that would make the matrix P non-invertible, which is what we don't want. Since D is a 2x2 triangular matrix, then that means the eigenvalues of A are the entries on matrix D's diagonals, which are 0 and 1 respectively. So multiplying everything through, I just get this 2x2 matrix A, which is diagonalizable because it has two distinct eigenvalues, but it is not invertible. And I know this because the determinant is equal to the product of its eigenvalues, and earlier we did establish that the eigenvalues of A were 0 and 1. That means that the determinant of A would be 0, and that makes it non-invertible. And I later verified this below. I also just checked my P matrix just to make sure it made sense. So essentially what I did was I just took the eigenvalues of A and found out the corresponding eigenvectors. And I saw that they were both linearly independent eigenvectors with a scalar multiple of 2 and 3. And because these two eigenvectors in the 2x2 matrix are linearly independent, then that means that these eigenvectors correspond to the columns of a matrix P, which I got down below here, finally. And that is equal to the matrix P I established in the example earlier. So in my example 2, and also my example 3, I took the same approach. So hopefully you can verify that. And that is all. Thank you for listening.